So I'm going to create a transaction signer. So there's a helper class called the transaction signer. Let me import that. Okay. I'm going to create an instance of the transaction signer because it's just going to be, and please don't judge me for this. I'm going to do some really ridiculous side effect programming which I coded into the library, but I beg you don't judge me. I'm going to modify the API at some point to return the signed transaction from transaction signer. Right now, what's going to happen is I'm going to pass in the spending transaction into the transaction signer. It's going to modify that transaction, and I'm just going to immediately afterwards use that modified transaction as if nothing happened. Not as if nothing happened, but this is an anti-pattern in programming. So please don't do stuff like this when you build your own APIs. I should not have done this either. I had reasons, or so I claim. But yes. Okay, so signing the transaction. So I'm going to sign the spending transaction, and what else do I need to do? Okay, in order to sign the transaction, I actually need to reference the output where the funds are coming from. So I'm going to say that hang on. Where is my funding output? Okay, I'll go and fetch the funding output in a minute. Okay, so I'm going to let's just say funding output, and the input index. So the funding output. Okay, I'll explain this in a second. We basically need the transaction on the left where Alice is spending from. That is called, I'm calling that the funding output, but you might have heard this term UTXO before. UTXO stands for unspent transaction output. It literally means that it is a transaction output that exists on the blockchain for which there is no corresponding spending transaction to the right of it on the blockchain, right? So there is no transaction that spends money from that output. One of the preconditions of the UTXO-based accounting model in Bitcoin is that when we create a spending transaction the way we are doing now, we have to spend all the coins from the output. We can't spend only a small or a partial amount of it and leave some behind. The output has to be completely consumed, created. We have to create a new transaction and do what we have done now, which is send money to one address, and all the money that we want back, we basically have to send the money back to our own address or to a new address that we also control. Or we can send, if we really feel generous, we can send the change to somebody else. What has to remain inviolate and what will be enforced by the consensus layer, by the mining network, is that all of the output has to be consumed by a corresponding transaction on the right. Yeah. So when we say funding output here, what we really mean is UTXO. So I could also have used the moniker UTXO. I'm going to say funding output because I like the word a little bit better, and the funding output has to come from the transaction that we're actually spending from. Now, we don't actually know which output in the transaction that Alice can spend from is the one that she can spend from. We have to go and look that up, and I will talk about how we look that up in a second. We're going to have to use the CLI tooling for this example again to go and do that. And the next parameter here is the input index that we are signing. So we've only got the one input that we're creating, so we're going to say we're signing input 0 in our transaction, and then we need the signing key, which is going to be Alice private key, and then the last part here. So let me wrap this around so that I can actually show you. I'm going to write this I'm going to write this a little differently so that it shows up on screen without wrapping off the screen. Okay, so the last thing that needs to be passed in is something called a SigHash type. So I'm going to combine fork ID and SigHash type of all. Remember that there are all of these fields in the transaction. So let me go. Okay, I'm going to take a stab at giving you the short, condensed version of this with a caveat. SigHash types are essentially the signature that we're going to be generating, right? When we create signatures, we are actually not signing over the serialized version of the serialized version of the transaction. The signature that we're generating, we're actually signing a hash value. That hash value is derived from a concatenation of certain fields from the transaction that we are creating, the new transaction we're creating on the right, and certain fields from the old transaction that we're spending from on the left. The SigHash type enumerated types, the combination of the enumerated values, specify which of those fields on the right hand side and on the left hand side we are going to be concatenating together to create the hash value that will be used as part of creating the ECDSA elliptic curve signature, right? The caveat is the explanation that I just gave you is is correct, but please, in order to get the full idea, because this is a super important topic, right? To get the full idea of what actually needs to happen and what's going on, please read this documentation over here. Please read everything about SigHash here to understand really clearly what each of the SigHash values mean, what the combinations of transactions are that are actually signed under certain conditions. The reason why this stuff is important is because specifying the wrong types of SigHash could lead to unintended consequences for the transaction that you might want, that you would have. SigHash type of all is SigHash type of all is fairly safe way of doing it, but please do read the documentation on SigHash types. The fork ID is something that you just have to add in here in order to. Okay, I'll have to explain this as well. If you go back and recall, in 2017, there was a split in the network between Bitcoin BTC and Bitcoin Cash. Subsequent to that split, there was a split between the Bitcoin Cash and the Bitcoin Cash network, then split into the Bitcoin Cash and the Bitcoin SV networks, right? So we had these three network splits, which I need to refer to. The fork ID value here is a form of replay protection that protects users from accidentally having their funds double spent on the two Bitcoin networks, which is Bitcoin Cash and Bitcoin BTC network. The fork ID value here does not provide any sort of replay protection between the Bitcoin Cash and the Bitcoin SV networks. We do need to specify this though, because the network, the consensus network, will not accept a SigHash type that does not contain the correct value with fork ID in it. So the Bitcoin SV network will not accept a transaction that does not have the fork ID value in there. It will only accept transactions with this fork ID value combined into the SigHash type as a way of distinguishing transactions that can't be spent onto the Bitcoin SV or the Bitcoin BTC network. I think I did a horrible job of explaining that. Let me say that again. In order to clearly distinguish the transactions that the UTXOs that can be spent onto the Bitcoin SV network versus the UTXOs that can be spent onto the Bitcoin BTC network, this fork ID value is needed. This fork ID value will be enforced at the consensus level by the miners. So the miners will not accept your transaction if it contains the fork ID on the BTC network. The miners won't accept the transaction. If it lacks the fork ID on the Bitcoin SV network, the miners will not accept your transaction. The reason why I did not hide this in the API for Bitcoin 4J is because it's important enough for you, the developer, to know about that I've surfaced it, so that you always have to remember to put it in there so that you can be explicit about what it is that you're doing, right? Because to an extent it is actually kind of possible to use this library to create transactions that could be validly spent on the BTC network as well. But don't tell anybody. No, seriously, if you I haven't tested the library for spending transactions on the Bitcoin BTC network, but technically it should be possible to create transactions using this library that can also be spent on the BTC network. The caveat there being, of course, that please, if you're going to create transactions that are spendable on the BTC network, stick to pay to script hash and pay to public key hash transactions. The library does not support segregated witness transactions, and of course the unbounded transaction types, which means anything goes on BSV, is not applicable to the BTC. So you will be constrained to those, but technically possible. This transaction ID we can actually now use to query the local node for the data that's associated with a transaction. So we can do that now. Let's go to the console. Say get transaction, right? So I want this, the raw transaction associated, with Ellis's with the funding transaction for Ellis, and then I want to decode this raw transaction. So there is actually an RPC command. So these are RPC commands which we are passing into Bitcoin CLI, and I'm going to pass the raw hexadecimal into decode raw transaction, which will then query the local node. And basically, not the local node, actually, I think Bitcoin CLI just knows how to parse this. We'll parse this, tease it out, and show it to us. You can also do this by just step debugging through the code, because we have actually ingested this raw transaction into the transaction class, if you recall. So you could just set a breakpoint, step debug through your code, and then interrogate the outputs to see the values from there, right? That's another way of doing it. So what we can do here is we need to look here, look at the outputs in this. So we have output 0. Here we can, so the output in Ellis's funding transaction that actually sent the money to Ellis is this one here, which sends 10 coins, and this address here, which is being decoded for us, should line up with Ellis's actual address. So if we go and look at Ellis's address, which is this one here, right? It lines up with this value here, which is the output at index 0. Now that I know it's transaction output 0 in the transaction, I can look at the funding output. I can just basically assign it to what they call the funding transaction, right? So the funding, Ellis's funding transaction has a series of outputs, and I can reference output 0 in there, right? And I can make sure that I've actually got the right type here by basically saying whatever you're inferring, I hope it's a transaction output, right? You can tell Kotlin. Last part, we have now signed the transaction. We need to get the raw version of this transaction to be able to broadcast it on a local network. And when we do this, we cross our fingers and hope that the local network accepts our transaction as being valid. We're going to see in a second. So where are we now? Okay, so we're going to serialize it. In order to actually dump it onto the console, the serialized function actually returns a byte array, but the byte array, there is a utility class as part of the Bitcoin for J library, which contains a convenience hexadecimal-encoder decoder. We want to encode this returned byte array to its hexadecimal representation, and then we want to print that hexadecimal representation onto the console. Right, let's run this. There we see the addresses are still being printed out, and here we have the actual hex, the raw hexadecimal transaction data being printed, right? So I'm going to go back to the terminal now. I'm going to clear the terminal, and then I'm going to ask it to send this raw transaction. You can only broadcast raw transactions once, and if they succeed, they succeed, and if they fail, they fail. Look at that, we've got a transaction ID back. Right, so I'm going to copy this transaction ID. Usually if you get a transaction ID back, kind of means you're okay, right? It means that the transaction has been accepted by the network. Now we don't have a block explorer for localhost. This is what we deal with. We've got a transaction ID back. With this transaction ID now, I can go and do what I did before, which is, okay, first I'm going to save the transaction ID. Please note that if you replicate this code on your own machine, the transaction IDs won't line up because the signatures that are generated inside the transaction won't line up, because you'll probably have different private keys if you do. And let me think, what else won't line up? The transaction IDs might not line up because of where you're spending from and various other things. So don't freak out if the transaction IDs don't line up. What you want is, at the end of the day, to be able to get a transaction ID out from when you're actually broadcasting the transaction on the local network, so that if you then go get raw transaction, right, which is not the one that I serialized, but I'm going to ask for the raw transaction that that is associated with this transaction ID on the network. And these two values should line up, but I'm going to decode this raw transaction which the node has given me back, which should be the transaction that I gave to it. So let's go decode this raw transaction that the node just gave me back. Nope, that's send raw transaction, Stefan. We want to decode raw transaction, right? So if I decode this, I want to see that everything lines up properly. Let's go to the top first. Now, remember that Alice is now Alice has received 10 coins, and she's trying to send 10,000 Satoshis to Bob. So there should be an output in this transaction that actually sends 10,000 Satoshis to Bob. And then the rest of that money should go back to Alice's address. Now, let's quickly scroll back up here and look at the addresses that we're expecting to line up with these outputs, right? So we've got Alice's address and Bob's address, right? So we should see two outputs for starters, one to Alice and one to Bob. All right? So let's look at the outputs. Vout, we have index 0. We have an output to this address, which actually lines up with Bob. There's the value of how much we're actually sending. It's 10,000 Satoshis. It's at index 0. And then we're seeing a 9.9 Bitcoin transaction output, which actually lines up with Alice's address. So Alice is sending the right amount back to herself. And everything looks in order. Now let's see where she's spending this money from. She's spending this money, she's using as input the transaction ID. The input is actually being spent, if we scroll back to the transaction ID that she's received funds from, right? So this transaction that she's now created is referencing the transaction that she was funded on. It is referencing the output, the first output, which is output 0, on the funding transaction as the one that this transaction is spending from. Yep. So this unlocking condition has been correctly signed by Alice. So obviously we have generated a proper signature. We can see that we've got the SigHash type all combined with fork ID in here as well. So all looks in order. We have successfully created a transaction. We have composed it from first principles, essentially, as it were, and we have now successfully broadcasted onto the local network. This is the same method that you would be using to send a transaction onto the wider network. You would find the transaction that you would want to spend coins from by asking from a miner, or by getting it in a peer-to-peer fashion from another party. They'll just give you the transaction. You'll take that transaction, and then you will construct the spending conditions from the output that you are authorized to spend from, because that output should be spending to an address for which you control the private key, so that when you create the spending transaction, your spending transaction will reference the on-chain transaction you're spending from. And then when you generate the raw transaction output and pass it onto the mining network, which will probably be a REST API, something like the merchant API, or an API that is published by somebody like What's on Chain or Tal, or Matterpool is another company that provides services like this. So in the absence of running your own public node, you can submit this raw transaction onto the public network, not this one, but the raw transaction that you created, onto the public network, and it should work, right? So as an exercise for you, the viewer, I would ask you to maybe do this. Go to twostack.org. Go to Bitcoin4J. Look at the sample application here. The sample application has been done in Java. The sample application actually shows you how to obtain public testnet Bitcoins from a faucet, how to use the What's on Chain API, as well as the What's on Chain public block explorer, to essentially do what I just did on the command line with querying the system for the outputs, etc. And then how to send coins between Alice and Bob. How you can fund Alice's account, and how you can then send the money from Alice's account to Bob's account. And this test is great, because with this test, you'll use simple tools like curl, for example, to move the money into one of these, into What's on Chain's API, basically. So you'll be using the public testnet. And once you're actually using the public testnet, you're one step away from changing variables in your code to using the mainnet, right? So that is it for this episode. I hope that you're still with us. And if you're still with us, congratulations for making it all the way through what I'm fairly certain is a pretty long episode at this point. So enjoy the rest of your day. Thank you for watching, and I'll see you for the next one. Bye.